So this is a second video on solving log and exponential equations in Chapter 6. I'm going to go ahead and take a look on this video at problems that have to do with some of the log properties, and we're going to go ahead and stay in logs on these problems. I think on the first video we dealt more with problems that were either exponential, that I could stay in exponential, or exponential that I could convert to a log. But in this video, we're going to go ahead and stay in logs. So in this particular problem, what we're going to do, it says here, if the equation has logs on both sides, let's see if we can use this property right here. And if we could only get the log base a of u equal to log base a of v form, then we could just say what we're taking the log of can be set equal to each other, u equals v. So I'm going to use the property, and I could refer you to the sheet where I'm looking at these properties, but I'm going to use the property that says that the coefficient in front of a log can be used as an exponent, or vice versa, an exponent on what you're taking the log of can be brought in front as a coefficient. And that is coming from, let's see, right here, rule number 5, that if you have x to the u, you could bring the u in front of the log like that, right? So I'm going to go ahead and take, in order to use this, by the way, you can't have any coefficient other than 1. So I'm going to take this 1/2 and bring it up, and I'll have the log base 3 of x to the 1/2. And I'm going to do the same thing here. I'll have the log base 3 of 2 to the 2nd power. I'm bringing this up as an exponent. So this now is going to be the log base 3 of x to the 1/2 is equal to the log base 3 of 4 because of 2 squared. And now I am ready to say that because I'm taking the log of both sides, I can just go ahead and set x to the 1/2 equal to 4. And if you remember fractional exponent discussions from earlier math classes, x to the 1/2 is the square root of x. And now I could square both sides to solve this problem. And x itself then must be 16. Okay, down here I only have a single log on a side. So what I'm going to do with that problem is, actually, this problem will go to exponents. I mentioned earlier I didn't think I was going to have any problems on here that would go to exponents, but this one will, and here's why. When you have a problem where what you're taking the log of has the unknown in it, it says if the unknown is in the domain of the log, and here's the input to the log problem, there's no way I can put this in my calculator. So I'm going to go ahead and then convert to a log and say, because the output to a log is a power, or an exponent, I'm going to say 3 to the 6th power is equal to 2x minus 3. I'm going to add 3 to the other side, and I'm going to divide by 2, and that is what x would be equal to right here, right? This would cancel, and that is what x would be equal to, and I could certainly put that in my calculator. I'm not going to take the time to do that, though. That'll be something that I think you should be able to handle without any problem. Let me just go down to the next problem here. And here's a problem that because I have a sum of logs on a side, I'm going to go ahead and use the property that allows me to put that into a single log. It says if the equation contains the sum or difference of logs, convert to a single log and go back to idea number 3 or 4, meaning that, for example, here, if you end up with a single log like this, then I could just convert it possibly to an exponential. Or if you end up having maybe a sum or difference on both sides, then you will have a problem like this, where you get a single log on each side, and then you handle it like this. So what I'm going to do here is I'm going to say that the sum of logs is equal to the log of their product of what we're taking the log of here. And so this is going to be the log base 10 of x times x plus 15, right? The log of the product is equal to the sum of the logs. And by the way, I'm using rule number or property number 3 right here, that if you have a log of a product, it's equal to the sum of the logs of their factors, right? Of the factors here, x and the log of y. But I reversed it. I said then, okay, if I start with the sum of logs, I can call it a single log of the product of these two domains right here, right? The inputs. And so that's what I have, and then it's equal to 2. And now I really can convert this. I'm going to use the idea that's up here in number 4 where I have a single log. And I'm going to say, well, because the answer to a log is an exponent, I'm going to say 10 to the second power is equal to x times x plus 15. And this is 100. And I'm going to distribute here and get x squared plus 15x. And maybe something we weren't expecting to happen has occurred here because we ended up with a quadratic. So I'm going to go ahead, and whenever I solve a quadratic, usually I go ahead and set it equal to 0 and try factoring or the quadratic formula. It turns out if I brought that 100 over to the other side, I would have x squared plus 15x minus 100. And this happens to factor because the two numbers are multiplied to negative 100 and add to 15 are 20 and negative 5. So I could factor this into x plus 20 and x minus 5. That would give me negative 100, and 20x minus 5x would give me 15x. And now I use the zero product property, which says if you have factors that multiply to 0, then either of the factors could have been what produced 0. Oops, I already solved that in my head here, but I wanted to write the original factor of x minus 5 equals 0. And now I solve these and I get x is equal to negative 20, or x is equal to 5. By the way, I would end up eventually eliminating this right here because you cannot take the log of a negative number. Let me just show you if you went and tried to put this in here. Go ahead and check it in your original. Solutions should always work in original equations because in the process of solving the equation, you may have manipulated it so that some answers that come out don't really work in the original equation. But if you take a look here, if you put negative 20 right here, watch what happens. You'd have this, the log base 10 of negative 20 plus the log base 10 of negative 20 plus 15. And the question is, will that ever equal 2? And the truth is, no, it won't, because 10 to what power is going to give you a negative number? It doesn't matter, even if you use a negative power, you won't get a negative result. For example, 10 to the negative second is still a positive answer. That's 1 over 10 squared is equal to 1 over 100. I mean, no negative number in the exponent is going to go ahead, and that's what a log is an exponent. Even negative answers to logs aren't going to produce negative results, and so this is not going to work. So this is not a solution. Now 5, I bet, is a solution, and as long as we're checking things, we could check on that. Let's just go ahead and put that in there. Maybe I'll just go ahead and section this off like this. So let's check on 5. So let's put 5 in there. We would get what? The log base 10 of 5 plus the log base 10 of 5 plus 15. And the question is, does that equal 2? Well, I'd go ahead and want to put this in my calculator, and let's just test this out here. So we're going to have this plus the log base 10 of 20. And by the way, we don't even really need a calculator because this is the sum of logs. And we know that the sum of logs, we just use this property over here, right? The sum of logs is equal to the log of the product of these two domains. So what we would have here is the log base 10 of 5 times 20. Right? So the log of a product is equal to the sum of the logs of their individual factors. And we're going to get a log base 10 of 100. And it turns out, since the answer to a log is a power, and that power should answer the following question: 10 to what power gives me 100? To the second power. So that one did work. And so this is a solution.